Okay. Oops. That's still working? Okay, good. So the stragglers that are coming in, they can go up through the top. And I just noticed for the speakers that are here, the water, if you need one, is actually hiding underneath there. So it's the secret place. So we're now into session 2. And I'll soon turn it over to John Lienhard, who's the faculty director for J-WAFS, or the Abdul, Latif, Jameel World Water and Food Security Lab. Similar to last time, so we'll hold questions to the end, and then we'll do a panel discussion. But John, thank you for your time today, and please come on up and take it away. Okay. Thank you.
Do you ever wish that music played when you walked into a room, you know? Something like that. Good morning, everyone. It's good to see you all here. As Brian said, I direct J-WAFS, the Abdul Latif Jameel World Water and Food Security Lab here at MIT. Our executive director, Renee Robbins, is somewhere up in the very back row. And we also have a table out front that's got some brochures and other information if you want to dig a little deeper. J-WAFS is interested in the spectrum of problems around the human need for water and food in the face of rising population, changing climate, and growing standards of living. For instance, we are interested in how you can provide more water sustainably, more fresh water sustainably, as exemplified by this wind-driven desalination plant in the Canary Islands, shown in my figure here. We've been very interested in the impact of climate change on food production and on the impact of food production on climate. In fact, we recently had a major workshop last month, which will produce a report on this topic, asking how will our food production need to adapt in the face of a changing climate? How will it rise or fall? And what might we do in terms of altering food production or diet in order to mitigate climate change? We've been very interested as well in advanced technologies for purifying water, for removing emerging contaminants at low concentrations, for sensing the presence of bacteria or heavy metals in water and food, and a range of technologies in that domain. And there's a lot happening there at MIT, and that's mostly what we'll focus on in this session. And finally, we've been interested in the deployment of these technologies, both in the first world for industrial application, as well as in the developing world. And we're interested in the question of how something invented here can be designed in such a way as to be adopted in a place where it's really needed. Structurally, J-WAFS is an institute-level entity. We work with all departments and schools at MIT. In fact, the word lab in our name needs a little explanation. We're a lab in MIT parlance. It means an interdepartmental, interschool organization that serves to bridge activities amongst many separate units. We are funding all schools at MIT at this point. We work with most departments, labs, and centers. And the question comes up, how many faculty are in J-WAFS? J-WAFS is not an academic unit. And in fact, we work with faculty whose residence is the various departments and schools. So functionally speaking, we have up to 1,000 faculty in J-WAFS, depending on who proposes and who has ideas of interest to these problems. The way we're structured is principally around research. Our primary mission is to support and catalyze research, innovation, and technology deployment. We operate a seed grant program that funds about $1.5 million a year in grants to faculty at MIT. These cover the full range of topics under water and food. We have a competitive proposal review process, NSF style in its activity, that down selects which ones are ultimately picked. We have a program for tech transfer where we work with MIT's Deshpande program on early stage ideas, early stage technologies around water and food, things that might spin out and become companies. We have a couple of examples of those that we'll talk about today as well. We sponsor research directly, particularly through our Research Affiliates program, and we also conduct expert workshops around topics such as climate change in food or renewable desalination or other issues of interest. In terms of student support, we work with the MIT Food and Agribusiness Club. We work with the MIT Water Club. We support business plan competitions that they run. We help them connect to sponsors, and they, in turn, organize events on campus like the MIT Water Summit, like the Rabobank MIT Food and Agribusiness Innovation Prize. And then finally, we have a partnership program where companies who are interested in doing directed research around these topics can work with us to find appropriate PIs. For example, our research affiliates come to us with a set of problems. They say, these are things that are urgent to us. Could you help us find PIs? We socialize those ideas with relevant MIT faculty. The ones who have good suggestions can write a proposal, submit it back to the sponsor. The sponsor meets with them and picks the one that best fits their actual needs. And that's been effective as well. So I think I've said most of what's on this. We have the Research Affiliates Program. Any of you who are interested, please chat with me or Renee. We also are interested in research consortia around topics of common interest to multiple companies. Now, to give you some idea of the types of work we're doing in J-WAFS, I'm going to show a few examples. You'll actually hear from Professor Karnik in a few minutes, so I won't go into great detail here. But typically, when you want to sample water to see if it's safe to use, you'll fill up several liter bottles of water and you will take them to a lab. And if you're in a remote setting, that process can become quite arduous. Getting the samples down a bumpy road in remote India to a lab to be tested without damaging them, etc., is challenging. And so Professor Karnik will tell you about some work he's been doing with others to develop a dry sampling technique where you can actually put a sample on a card and mail it. Much easier. We are interested in food safety. We do a number of different projects that relate to sensing for bacteria or other contaminants in food. One project we have is a collaboration between Professor Hahn and EECS, Professor Liu at the Whitehead Institute. They're interested in a combination of microfluidic devices for concentrating samples together with bacteriophages that can infect pathogenic bacteria and make them bioluminesce. And so they've been developing some really interesting ideas in that direction. We have supported as well a project that's looking at the overuse of antibiotics in imported meats. You have a lot of antibiotics that can be fed to, say, chickens being raised by a small farmer in China. Not all antibiotics play well together, and in fact, if you get the wrong families of antibiotics together, you get toxicity. This team has been looking at developing assays not for every possible antibiotic that was used, but for signs of toxicity within the meat itself, so that you can check more easily for these types of problems. Back to the subject of food safety, you'll hear from Professor Tim Swager in just a moment. I think I'm going to say almost nothing about this since Tim is the very next speaker. We've been supporting collaboration between Professor Strano and Professor Sinsky to look at carbon nanotubes as sensors for various things, broadband assay, can sense for heavy metals, can sense for bacteria, can sense for allergens by changing the fluorescence of specially coated nanotubes. Their concept is to have something like a microscope slide that's got maybe 96 different dots on it for differently coated nanotubes. You put a drop of water on this, some of them will light up, some won't, and it can be detected with very inexpensive instrumentation. This is also a project moving toward commercialization. And then also in the area of food safety, we've been working in India, in this case, with Professor Sanjay Sharma. The problem here is about milk production. Milk is produced in India through a widely distributed supply chain, coming up through very small farms, 2-3 cows, and then aggregated repeatedly until it eventually gets to centralized distribution. The potential for adulteration or other contamination of milk at each step is high, and so you want a simple and effective way to test milk every time it's aggregated. They've been developing a very inexpensive sensor that can be used locally to test for casein and milk fat separately and to give you a marker for whether milk may have been adulterated. This will be commercialized as well. Amongst our graduate student fellows, you will hear today from ZJ Tang. He will talk about some work he's been doing using developing living materials that can respond to environmental contaminants and give you a simple way to check for the safety, for example, of drinking water. So that, in a quick whirlwind nutshell, is an idea of what we do at J-WAFS. The next 3 presentations will all be related to work that we're supporting here at MIT, and I'll let the speakers tell you about these themselves. That being said, I'd like to introduce the first speaker in this panel, that being Professor Tim Swalker. Tim is the John D. MacArthur Professor of Chemistry here in the Department of Chemistry and the Director of the MIT Despande Program.
Okay, thank you. Yeah, thank you, John, for the introduction and also outline J-WAFS program. So as John mentioned, the work I'm going to talk about today was supported by the J-WAFS Solutions Fund, which is a fund that is for translational type research, and it's also in collaboration with the Despande Center, which I direct, which is also another nice thing about MIT is where all these different organizations can complement and work together and assist each other in making these things happen. So that's just one of the great things that happens here at MIT. So I'm going to tell you a story about what I call dynamic droplets, and you can maybe guess here toward the end how I actually make this, how we made this image, where we have essentially looks like a bunch of flying saucers attacking somewhere from an old sci-fi movie. But we start here with sensing. So basically, our group does a number of different things, but everything usually kind of comes back to sensing somehow. And in thinking about how you do biosensors, you really have to think about how do cells work. Well, they're really fluid objects. They have fluid on the inside. These membranes are technically organized fluids from a thermodynamic standpoint, but they have often a lot of these receptors, proteins that can aggregate, that can move around, that are glycosylated often or phosphorylated, kind of upregulating, downregulating, making communication, knowing who's next to it. And so this idea was, if we're going to emulate or we're going to sense biological species, maybe we should try and emulate that with our own fluid system. And so what I'm going to tell you about are complex droplets. What I'm showing you here is a polydispersed droplets dispersed in water. The red phase is the organic phase, and the gray phase and around it is a fluorocarbon phase. So these are essentially spheres inside of a sphere, and they are essentially organized by using different interfacial tensions, using surfactants. And so if you want the fluorocarbon sphere on the outside, use a fluorocarbon surfactant. Okay, so the fluorocarbon's on the outside. You want the hydrocarbon on the outside, use a hydrocarbon surfactant. And what we found in developing new ways to make these droplets in this kind of precise fashion, we came up with essentially a more efficient way to manufacture them. We also found that we could essentially turn them inside out and not have them come apart. And so what we have here on this side, we have a droplet. This is how it was given birth to. It has the fluorocarbon on the inside, the hydrocarbon on the outside. But if we add a bunch of our fluorocarbon surfactant, we essentially can invert those phases, turn them inside out. And here in the middle, this is a microscope image looking down. And here in the middle, you find a very special type of droplet I'm going to tell you more about called a Janus droplet. And the reason you don't see this on its edge is it's being aligned by gravity. So essentially the density here, difference between the fluorocarbon being more dense than the hydrocarbon, creates an aligning force on this that allows us to organize these optic elements. And just to show you kind of chemically how you can start triggering these events, here's a case now with polydispersed droplets, which are very easy to make. You can just basically shake things up. We have to do this at elevated temperature where we get essentially an upper critical solution temperature of our two phases to make all the droplets the same composition. But here you have a case where we have a surfactant that's protonated once at neutral pH, but if you go to a lower pH or higher acidity, we can protonate basically both, and we can basically invert these different phases. And again, you see right here in the very middle, you see that Janus. You don't see it because it's aligned. Similarly here, this is a hydrolysis reaction. We basically have something that's a surfactant, and as we transition it, it goes through a Janus and then basically inverts. We're just basically degrading our surfactant here. Now, how do we go about making sensors from these? Well, we're going to use the refractory optical properties of these droplets. And this is shown very nicely here by something that Lucas Zeiniger and our group put together, where he basically had a bunch of droplets that have two phases in them. Fluorocarbon phases are slightly lower index in water. Hydrocarbon phases tend to be higher. And because they're different from water, they scatter, and it looks like milk. But if you heat this up to where we get above what we call the upper critical solution temperature, where this goes to one phase, which is actually how we manufacture these types of materials, what you can see is he's adjusted this to where the indice on average here is exactly that of water, so now you can't see it. So it turns out that that these droplets have more than just scattering properties. They can be quite special, particularly with this alignment. And this is something that we've teamed up with Matthias Kolla, who is in mechanical engineering, and he's an expert in refractory optics. And basically everything I'll show you, most of the things I'll show you from here on, he's had a big influence in our group. But this is some modeling that his student Sarah Nagelberg put together, and is showing that these droplets actually behave as lenses. So you project light through them. The Janus, as you see, essentially has an infinite focal length. That is, it transmits directional light in one direction. These other ones can be focusing, or they can essentially give divergent light. And so, what we're interested in doing is making use of these different properties to create sensors, and in particular biosensors. And so we're very interested in pathogenic organisms that can be contaminants in food, like E. coli or Salmonella. I'll tell you about both of those, but there are other ones, and including viruses. And one of the things that these organisms have is they have affinities for different types of carbohydrates. You can also use other types of recognition elements in conjunction with carbohydrates. What I'm going to show you first is just kind of how we can use carbohydrates, particularly E. coli is interested in mannose, to detect these. So what we do is we just make a very simple surfactant. We make mannose coating our organic phase, and the bacteria bind to mannose in what we call a multivalent fashion. That is, many different mannoses bind to a given bacteria. And so they basically hook many of them together. And you can emulate that just by using just a small protein that basically comes out of these types of recognition elements that happen in bacteria. It's called concanavalin. And it binds 4 equivalents of mannose. So you take our droplets, remember they're aligned with gravity. They look like this under a microscope. I'll show you what they look like normally, just visually in a moment. But if you take this and you just give it just a little tap, just shake it around, the concanavalin essentially glues these things together, and you get something called an agglutination event. And this will not revert back. And why this is important is now what we have is something that can give you a very, very simple way to detect things. In fact, is what we're showing here is the QR code. This, again, light is transmitted. Gets some distortion to it, but it's transmitted. And then here we have very highly scattering objects, and we can basically get a detection event. And we've applied this to basically use this same sort of event to detect the same sort of analysis, just reading a QR code with a cell phone to detect bacteria, and that's in this E. coli in particular. We can also use a very small lens on the front end of your camera and do image analysis and essentially quantify this data. So I showed that the QR code is clearly binary, just on, off, or some threshold detection. You can get quantitative detection just by doing simple image analysis, and this holds up to basically gives you nice quantitative analytical data. So the last part I want to tell you about a newer area in the group, a newer effort, where we're now taking these droplets and we're putting essentially, rather than transmitting light through them, we're making light come from within them by putting fluorophores inside of them. And this is just a very robust kind of standard fluorophore we can put here. And our first thought, what we first went after was, let's just make a waveguide. It's kind of a little hard to see here, but there's a little piece of glass here. And to see how we can basically change the fluorescence of this dye that's in the red phase by changing the essentially morphology of these droplets. Because when it's in this morphology, they got the low index fluorocarbon phase there that has no dye in it, and it doesn't couple the light into it well. But here it couples the light into it. And we can make it a simple little waveguide or just a prism type device and show how we can essentially change this as a function of surfactant. And we've actually developing some sensors for even caffeine analysis that can make use of these types of kind of tilting or changing morphology. I want to show you in the very last part today a new method that we come up with for detection of pathogens using this fluorescence method. And it came really out of doing some experiments. We didn't really understand what was going on, so we went and talked to Sarah, who again works for Matthias Kola in mechanical engineering. And she started doing essentially these ray diagrams on these complicated droplets. And the light, you can see the light coming out of this red phase varies in direction as a function of morphology. And so what we've done is we've triggered this with essentially an antibody assay here, or carbohydrates, both work, and essentially to remove those by exposure to a pathogen and then change the interfacial tensions and change morphology. This works as a prototype of a device that we have that does this. We just simply put a fiber optic over the top and measure directional emission from this. And one of the things that's really gratifying about this, when we do this directional emission and we actually change the morphology of these droplets, you can see we get this plot we call the L curve, or light curve, or we actually call it Lucas curve because Lucas is the one that first came up with this. But you can see that the calculated and experimental data is extremely is well behaved. Essentially, we know computationally why this is happening. And so the scheme here is that we can work around this different L curve by essentially changing morphology, just measuring directional emission topwise from these. And these are what the droplets essentially look like against side-on images. And Lucas and Chi Fong have been working on different applications of this. I'll show you this last real technical slide here that we've been able to extend this now to detect salmonella. It's relatively, most problems with food-borne pathogens is really time-consuming to detect them. It takes hours, which is not coincident with manufacturing when you need to get things off into the grocery stores. So this is relatively fast, in less than 2 hours. And we're pushing the detection limits down below 100. We think we can get down to single pathogen detection limits with this method eventually. But we're definitely in regions where it's very useful for different types of food and beverage types of applications now. And so I've just showed you this story here, kind of, scattering particles, waveguides. We have more on that. And now these essentially directional emission. And what's really key is our funding, which again, thank you to J-WAFS for this. Actually, E&I, which is a member of the Energy Initiative, actually funded early parts of this work because we are interested in using these droplets to deposit electronic materials also. So thanks to them. And I have it's a little bit of an older picture, but it shows some of the people that really started getting this research going in it. And I want to particularly acknowledge my collaborator, Matthias Kola, and his student, Sarah, who have been really instrumental in this. And I will not take any questions now, but later. Thank you.